Okay, kids, so we're back. We're still in section 2.3, section 2.4. We're just going to go over some really important examples of two-dimensional dynamic situations. And one of the classic ones is called an inclined plane, also known as a ramp. And it's used a lot in first year university physics courses. So let's draw the ramp. Here it is. Okay, I'll try to draw it as straight as I can. Not too bad. And what we know about this ramp is that there's an angle here, theta. And we also know that on this ramp is an object. There it is. Now what we want to do is talk about this object as it's sliding down the ramp. Sometimes we talk about that. Sometimes the object will be static. It's not moving. Sometimes the object will be sliding up the ramp. Maybe someone has given it an initial velocity and it's sliding up, things like that. So these are all situations that can exist with this setup, this ramp with an object on it. And the other thing that's usually given to us in these problems is that this surface, the sliding surface, usually has some known coefficient of friction. So depending on the question, you could be given the coefficient of kinetic friction. You could be given the coefficient of static friction. Depends on the question. Sometimes they give you both. And really what you should do when you're looking at this question is draw a free body diagram for this object. So we're going to do that. So right off the bat, there's a surface here. So there will be a normal force. Now remember, the normal force is always perpendicular to the surface. So there's going to be a 90-degree angle between this normal force and the surface. Next, let's assume that in this situation, the object is sliding downward. So since that's the situation, it's sliding, it's moving, there's going to be a frictional force. Now since it's moving, it's a force of kinetic friction, and kinetic friction always works against the motion. So it's going to be up the ramp. And lastly, since we're on the planet Earth, there's a force of gravity acting on this object. And we know that's mass of the object times the gravitational field strength. And I remind you, that is also known as weight. Okay? So if you take a look here, the object is going to slide down the plane here. So in order to solve this problem, it is a two-dimensional problem. If you think about setting up a reference frame, and the normal reference frame we would set up is like this, none of these directions are very common in the motion of the object. The object's actually sliding down the plane. So in this situation, this orientation just does not work. So what usually happens is they just twist the Cartesian plane, which you're allowed to do. Do it to your convenience. And x hat, positive x hat, is down the plane, and positive y hat is up from the plane perpendicular to it. So this is something brand new for us, having this Cartesian plane x hat, y hat, oriented in this way. And that leads to something you've never seen before. If you take a look at the forces involved here, F normal, the normal force, is absolutely positively in the positive y hat direction. The force of kinetic friction is absolutely positively in the negative x hat direction. But when you look at the force of gravity, it doesn't align itself with x hat or y hat. So this is a strange situation where you actually have to break gravity down, as odd as this may sound, into an x component and a y component. You've never done anything like that. So there will be a force of gravity x component. Let's make a better x there. And a force of gravity y component. Now let's just remind us of what the angles are in here. That's 90 degrees in there. That's theta, so this would be its complement to theta, which we'll call phi. And when I say complement to theta, what I mean is that theta plus the phi have to equal 90 degrees. Okay? You know that in a triangle, you've got 90 degrees from here, so the other two have to be 90 degrees because they have to equal 180 degrees. So if you take a look at that triangle and now try to analyze it within this triangle, you will see that there is 90 degrees right in here. So since there's 90 degrees right in there, that means this angle here has to be phi. Now, if you take a look at this triangle right in here, the triangle that's formed by force of gravity x component, force of gravity y component, there's a 90-degree right in here when we finish off this triangle because it goes straight up and down. This line here would be this that shows force of gravity in its fullness is perpendicular to this side of the triangle. So that means on the other side here, you've got to have 90 degrees as well, which then forces this angle here to be theta, to be theta. Now, when we are studying these problems here, it's really important to take your time, draw a proper diagram, right? Take a moment to think about what you're doing, because this is a movement away from our regular orientation of the x hat, y hat Cartesian plane. Now, the other thing that usually happens in this problem is you have to think about this object sliding down the ramp. So since it's sliding down the ramp, it's being pulled by gravity, or this component of it, force of gravity x, and there's a force of friction, kinetic friction working against it, but the object is not moving off the plane or crashing into the plane. There is no motion in the y hat direction, none. All the motion is in the x hat direction. So we can safely say that acceleration y component is 0 in these situations. Acceleration x component is usually something they ask you to calculate in these problems. The two things they usually ask you to find in these problems, but not always, but the common things they ask you to calculate for is acceleration, x direction, and what is the normal force? What is the normal force? That's the other thing they usually ask you to calculate. Now, when we try to solve for these, so these would be our required here, all right, when we try to solve for these questions in our analysis, we have to remember that we're going to use Newton's second law. This is still a dynamics problem. But since this is a two-dimensional dynamics problem, we have to break down Newton's second law into the x hat and y hat components. So breaking these down into components, it means sum of all forces, their x components, which is another way of saying F net x component is equal to the mass of the object times acceleration x component. And then over here, sum of all forces, their y component of that, is equal to F net y component, which is equal to mass times acceleration in the y direction. So we got required here, we got analysis, so I really should write G here. G for given, all right? Now let's assume here that the mass here, let's assume the mass is 1 kilogram. Let's assume theta is, I don't know, 40 degrees, okay? And let's say that the mu k coefficient of kinetic friction is 0.1. So now we have a complete given. We have our given, we have our required, and we have our analysis. So if you take a look here, well, maybe I went down a little bit too far there. If you take a look here, when you're looking at the x direction, you've got force of gravity x component, right? Plus force of kinetic friction is equal to mass times acceleration x direction. And over here, you're going to have a normal force plus force of gravity y component is equal to mass times acceleration in the y direction, which we have, through our discussion, decided that that is 0 because there's no motion up or down in the y direction. Best to say in the y direction. All right, so now what I'm going to suggest we do, and we use this example in the second sleigh problem, is drop the vector notation. Okay, drop the vector notation, and then later on, when you do your substituting, everything you substitute in will be positive. So what we're really going to do here is get our direction from the free body diagram. So force of gravity x component, that's a positive direction. And I drop the vector notation. It makes substituting a lot easier later. Force of kinetic friction, look, we're getting this negative direction from the free body diagram. We're dropping the vector notation. Force of gravity, normal force, that's up the y-axis, positive, so that's positive, the normal force. Oops, let me get a better end there. There we go. And force of gravity, y component, look at it. It's down towards the negative y hat direction. So negative force of gravity, y component is equal to 0. So let's continue on to the next line here. Positive force of gravity x component is minus mu k times the normal force. We don't need to use absolute value signs here because we already got rid of the vector sense of this. Mu k normal force is equal to mass times acceleration in the x direction. Then over here, we can have positive normal force, and I'm going to bring this to the other side, right? So that's going to change its sign. Equals plus force of gravity y component. So the next thing we have to do here is try to come up with expressions for force of gravity x component, force of gravity y component, by using the triangle that involves those two components, and here the full force of gravity vector, which I have in purple. And basically what we're doing is we're breaking force of gravity down into components using cosine and sine law. Cosine and sine, I beg your pardon. So take a look at force of gravity x component. It's towards the positive x hat direction down the plane. It is most definitely opposite to theta. So it becomes magnitude of force of gravity times sine theta, and that'll be in the x hat direction. And over here, if you take a look at the y component of this force of gravity, this FGY is adjacent to the theta, so it'll be force of gravity cos theta in the uh, negative y hat direction. So I'm going to put a negative sign there. Okay? So it's really important that you, like in any other question where you're solving things by breaking things down into components, that you, force of gravity is the only force that doesn't align itself completely in y or x. So I have to break it down into components. So it's really important to do that because we're going to need that in our equation soon. So if we look here, hey, we might be able to calculate the normal force. Why? Well, because I want the magnitude. Notice there's no vector sign here. I want the magnitude of force of gravity y direction. Well, if I just take magnitudes, it'll just be force of gravity, all positive substitutions, right, times cos theta multiplied by cos theta. And that would mean that the normal force is equal, better put a plus sign there because that's where we're getting our direction from. Positive force of gravity is just mg. Notice I'm not putting a vector sign here because I'm going to substitute in positive values. The direction has been taken care of by the signs I put out front. Cos theta. Okay, so we did the analysis there. Let me extend this page. And now we can start to do some substituting. So normal force is equal to positive, and I think it was 1 kilogram times, I'm not putting negative in, negative 9.8 newtons per kilogram. Remember, the direction's been taken care of by putting the symbols in. We dropped the vector notation. And the cosine of 40 degrees, okay? So put that in your calculator, see what you get. So I hope you got that this would be positive 7.5 newtons. And if you want to return to full vector notation, you could say normal force is positive 7.5 newtons y hat. Remember, we dropped the vector notation, so all we did there was calculate the magnitude. You can go back and look at the free body diagram, to find the direction. So now we can come over to this side here, and we know that force of gravity x component, right? All we want is the magnitude. All we want is the magnitude. So if I go back to the free body diagram, there it is. But all I want is the magnitude. So all I need is Fg sine theta. The direction's been taken care of already. I already did that. So Fg sine theta. Just like this one here was positive Fg uh, cos theta, this is positive Fg sine theta. Minus mu k times the normal force is equal to mass times acceleration in the x direction. Now I know what Fg is. That's mass times the gravitational field strength. So I finish off the equation here. Now I'm going to divide both sides by m. So both sides are going to be divided by m. So I'm dividing this term by m, the first term right here. I'm dividing that term by m, and I'm dividing that term by m, and I'm dividing that term by m. So let's do that. So there's an m in here, so that'll, oops, let me get the blue pen out. So that'll cancel out the m. So I'm left with g sine theta minus mu k times the normal force. Now there's no m to cancel here. And if I divide this by m, it'll cancel out the m. And lo and behold, I'm left with an expression that I can now substitute in. Remember, all substitutions here are going to be positive. Our direction came from looking at the free body diagram. So 9.8 newtons per kilogram, sine of 40 degrees, minus, I think that was 0.1. What's the normal force? Okay, 7.5 newtons all over the 1 kilogram. And that's going to be acceleration in the x direction, or at least the magnitude of it. So plug that in with your calculator and see what you get. And we'll be right back. Okay, so I hope you plug that in and we get plus 5.5 meters per second squared equals acceleration in the x direction. Now you might be wondering, sir, there's a Newton per kilogram here, a Newton per kilogram here. How do you convert that to meters per second squared? Well, newtons per kilogram is equal to meters per second squared. You have to remember a Newton, F, right? F, that equals M, which is, excuse me, let me fix that. F net is equal to M, which is measured in kilograms, right? M times A, meters per second squared. You still have a kilogram from the denominator. It cancels out. You're left with meters per second squared. So that's okay. And then you can write out the solution here and bring back the vector notation. Acceleration in the x hat direction is positive 5.5 meters per second squared x hat. And we've solved this problem. And once again, we've used this way of substituting in positive values because we made a change right here and right here, dropping the vectors, just talking about their magnitudes and looking at the free body diagram to establish the direction of the vectors. It's a lot easier to do it this way. Okay, now we're going to move on to the next example. Okay, so another classic example, you see this one used a lot in different physics courses, is very common. So maybe I can get my pen to work here. There we go. And it's a pulley with two masses. And it's also known as the Atwood machine. Okay, so let me draw what this is going to look like. A pulley is just a wheel. It's a wheel, and we're going to assume there's no friction as this wheel turns. And on the wheel, you put string. And hanging off one string is mass number 1, and hanging off the other string is mass number 2. Now, just for the sake of simplicity here, we're going to say there's no friction. and that mass of the second object is greater than mass of the first object. Now I've put in a video link to actually see a real Atwood machine work, so you can see a video. I think it's from MIT, pretty good school down in the States. And just to be even more specific, let's say mass of the second object is 10 kilograms. Mass of the first object is 5 kilograms. And what's going to happen is this object is going to accelerate upward. Come on now. There we go. And this object is going to accelerate downward. That can get very complicated mathematically speaking if you've got basically the same acceleration going on for two objects, but the object's accelerating upwards, the other accelerating downward. We need to find a way to come up with a reference frame that makes the mathematics easier. And the way you do that is you simply say, look, this is really a one-dimensional problem, with this being the positive direction of motion. It is a one-dimensional problem. But that one dimension is curved. So it's a curved dimension, and it curves along with the string around the pulley. That's really the way you want to approach this problem. So this could be like what you would put down as a given if eventually you will solve a problem like that. Now, what do they usually ask in these problems, these Atwood machine problems? They usually ask you to calculate the acceleration. Now, this would be a positive direction for acceleration here. This would also be a positive direction for acceleration. We're having this curved one-dimensional motion to make the mathematics easier. It's convenient. So usually they ask you to calculate the acceleration, and then usually they ask you to calculate the tension or the force of tension in the string that connects these two masses. Now, the one thing you have to realize, there's an old rule. If there's, oops, let me erase that, wrote down the wrong word. If there's one string, it feels the same dimension, the same tension through all of it. One string leads to one tension. If you have two strings, there's two tensions. Three strings, three tensions. But here there's only one string. You can't have part of it feeling really tight and the other end of it being loose. It doesn't work like that. So the tension that one experiences in terms of a magnitude of a force is the same for the other one. Okay, so the next thing we're going to do here is draw a free body diagram for each object. So we have force of gravity on the first object, and tension. Force of gravity on the second object, and tension. Now, these two tensions here, if you take a look at them, they're moving in the opposite directions here. Their magnitudes are the same, but their directions are opposite. So we're going to call this tension 1 and tension 2. But their magnitudes, probably a better way of saying this, their magnitudes are the same. Okay? It's probably best to put in here. It's the magnitude. More precise way of dealing with this issue. The magnitudes are the same, but definitely look, the tension on this one is going with the positive direction of the flow of the two objects, but this tension here is definitely going against it. So it's going to be tension 1, tension 2, knowing that in one string there's one tension with the same magnitude. But the directions are opposite here because they're on two different objects. So there's our given. There's our required. We drew free body diagrams as part of our given. And now we're going to look at analysis. Now the thing you need to remember in analysis is that this is a dynamics problem. So we're still going to use F net equals ma. That's the start of all dynamics problems. So you have F net on the first object is equal to the mass of the first object times the acceleration. And then F net on the second object, that's a horrible 2. Let me fix that. Is equal to mass of the second object times acceleration. Now the acceleration is going to be same for both of them because they're both accelerating in this positive direction of the string motion and the turning of the pulley. That's what we're going to consider to be the positive direction. Okay, so let's continue here. Let's continue with our analysis. So here you would have tension 1 plus force of gravity on the first object is equal to mass of the first object times acceleration. Tension 2 plus force of gravity 2 is equal to the second mass times that common acceleration. Excuse me. Now we have to keep this diagram in mind while we're doing all of this. And we're going to go back to our system of dropping vector notation and putting in the direction from the free body diagram. So if you take a look here, this is tension 1. And tension 1 has this magnitude. I'm just going to call it tension. And it's in a positive direction for the motion of this whole system. So I'm going to put positive tension in. If you take a look here, force of gravity on the first object, it's in the opposite direction of the flow here. So that would be negative force of gravity on the first object is equal to mass of the first object times acceleration. We're going to drop the vector notation. Tension 2, if you take a look at the diagram here, it's against the flow of this positive direction. It's against it. We know it has this magnitude, just T for tension. So I'm going to put in negative tension plus force of gravity on the second object is equal to second mass times acceleration, and we drop the vector notation. I'm going to drop the vector notation. So let's continue here. We know what force of gravity is. It's the mass of the first object times the gravitational field strength near the surface of the Earth. Notice no vector notation. Here, similarly, mass of the second object times the gravitational field strength. Okay, and what we're going to do now is we're going to name these equations. So I'm going to name this equation here equation number 1. There it is. And this here I'm going to name equation number 2. And if you take a look at this, kids, we've got a situation where we have two unknowns. The tension is an unknown, right? And the other unknown is the acceleration. Those are the unknowns. Okay? So what we can do is solve this by systems using methods of systems of equations. And one of the methods of systems of equation, you can do substitution, but another thing you can do, you probably remember this, is elimination, where you add the two equations. So here's equation 1. And to that equation, I'm going to add equation 2. And so positive t and negative t, that doesn't give me anything. I'm just going to add these equations. Let me draw an addition line here. So these two add together, positive t and negative t, well, that's 0. Then here we have m2g and minus m1g. I've added those two. And over here, I'm going to, on the other side of the equation, I'm going to add these two terms. And you see, the tension has been eliminated. The tension has been eliminated. So if you look at the left-hand side here, I can factor out a g. So g is factored out. And over here, I can factor out an a. So that's been factored out. Now I'm going to divide both sides by this sum, m1 plus m2. So I'm dividing both sides by that. And lo and behold, I have found a way to calculate acceleration. So the next thing we're going to do, and I'm going to ask you to do this, is substitute in the values and see what you get for the acceleration. Please try that. And I'll pause, you pause, and then we'll be right back. Okay here. So I've plugged in all the numbers. Notice in this method, when we drop the vector notation, we've talked about this a few times, right? All the substitution is positive, and I hope you got an answer of 3.3 meters per second squared. I hope that's what you got. So we still have to calculate tension, and that's where you take this newfound information, of acceleration, and we're going to substitute it. Oh, let me change color here. That'll be better. We're going to substitute it. There we go. Into equation 1. So take a look at equation 1. Positive tension, mass 1 is 10 kilograms. Oop, that's a mistake, isn't it? Mass 1 is 5 kilograms. Let's fix that. Mass 1 is 5 kilograms, not 10. So 5 kilograms, 9.8 newtons per kilogram. We don't plug any negatives in here. That's the new way of doing this. When we drop the vector notation, is equal to 5 kilograms times the acceleration we just got, which was 3.3 meters per second squared. And we're going to take this, bring it to the other side, and this negative sign will change to plus 5 kilograms times 9.8 newtons per kilogram. So I brought that over, and then to that we're going to add what was here already, 5 kilograms times 3.3 meters per second squared. Remember, meters per second squared is equivalent to newtons per kilogram. So try plugging that in, pause the video, see what you get. Okay, so we're back now, and we got 60. Oops, that's a horrible 6. Let's fix that. 66 newtons. All right, now that's the magnitude of that tension. We know that it's pulling in two different directions depending on which mass you're talking about. Okay, so we're going to continue on to another example after this. Okay, so here's the next example. It's the same one, same one. So that's the next example. But I suggest you go back and look in your textbook, and it talks about Newton's second law. And within Newton's second law, it says that the forces that you have to take into account are external forces, forces that come from outside of the object. So if you take a look at this whole thing as a system, there's the pulley, there's the string, and then there's two masses. If you take a look at it, well, force of gravity on the first object, that would be caused by the Earth. Force of gravity on the second object, that would be caused by the Earth. So they are external to this whole system. But these forces right here, they're in the string. So they're part of the internal mechanism. So if you really take a look at Newton's second law, technically, very specifically, you can, if you think about this question properly, you can ignore these. You can ignore these. And what uh, physicists have come up with a new way of thinking of this is saying, look, imagine the two masses as one mass with only the external forces acting on it. So here's this imaginary mass, which would be mass 1 plus mass 2. Consider them together. And then the only forces acting on it are external ones. Well, in one direction, we've got the force of gravity on the second object pulling it. On the other, in the other direction, there's the force of gravity on the first object pulling it. All right, and imagine that they're operating on this idealized imaginary mass. And then write F net equals ma for it, right? Well, that would be force of gravity 1 plus force of gravity 2 is equal to the new mass, which is the two of them added together. Now, let's drop the vector notation here for a second. So force of gravity 1 is down this way. So we're going to consider that to be the negative direction because we know the second object is heavier, so it's against the flow. It's against the flow of it. So let me get my pen back. There we go. So this is definitely a negative force of gravity 1. We've dropped the vector notation. And the force of gravity on object 2 is this direction. It's with the normal flow of this, which we decided to be positive. So this would be positive force of gravity 2. And that equals m1 plus m2, this mass of this imaginary object. And we're dropping the vector notation. Well, the force of gravity on the first object is simply m1g. The force of gravity on the second object is m2g. So let's finish off the equation here. Now I'm going to factor out a g, and I get m2 minus m1 is equal to m1 plus m2 times the acceleration. Now I'm going to divide both sides by this m1 plus m2. And we get g m2 minus m1 all over m1 plus m2, and that is equal to the acceleration. Now this should look very familiar. Is this not exactly the same equation we got from the other method? Let's see. Where's that equation? There it is, right there, and it's exactly the same equation. Exactly the same, okay? So this is just another way of thinking of this. You got to use your imagination, but it's completely legitimate. Okay, so we'll get to some other examples in the next video. Okay, thank you.